Haha, but that you can just discuss with them offline, right? You don't have to. Yeah. So yeah, so whenever you do it, okay. The other thing I wanted to mention is while we're waiting for a couple of people to come, is we are going to shift the class timings. Did the academic office inform you? Apparently, there's a class on Monday which is non-equilibrium or open quantum systems, which is happening at the same time. And there are some students there who want to take it, and maybe there's some students here who want to take that class. So we are thinking of, sorry, 1 second. I was just putting it on do not disturb. Just 1 second. So we want to actually shift the class to Friday, which is same time, 11:30 to 1. What? Not good? Oh, I see. No, evening is doesn't work generally. I see. Okay, then maybe we'll. Okay. Huh? Oh, I see. Maybe we should tell the academic office before they make the change final. I see, because we didn't see on the ICTS calendar that there's any other overlap happening there. What about 11:30 to 1 on other days? Are there classes every day and 2 to 3:30? Okay. So I will ask the academic office after this. We already told them to switch, but maybe you should tell them. If you're there, can you just quickly tell the academic office, if I hope they have not sent an email yet, right? Just tell them to maybe hold off on sending the email, and because I don't have them, that we will talk to them again. But they should not already send an email saying switch the course. Yeah, fine. Okay, so this we will try and do. So what are the times? Thursday is okay for everyone? Not okay. Okay. What about okay, Monday, Tuesday? In principle, we could do 9:30 to 11. That's not so great, but Tuesday 2 to 3:30. I thought there was some clash with something else. With what? That is on Monday and Tuesday. Okay, fine. I'll go look at the thing. What about there's ISC? You're saying Friday doesn't work. What time is your class there? 11:30 to 1. Okay. And how many of you have the class? Okay, and okay, but three people. Okay. Okay, fine. What other IISc classes are there? Because that we won't see on our calendar, on the ICTS academic calendar. Who is who? At what time? What day? 8:30 to 10. I see. Tuesday, Thursday, 8:30 to 10, and you're Friday. And what other day? 9:30 to 11. No, 11:30 to 1. Okay. Maybe if you guys, how to do this? How do we collect all the info? That's it? Only 2 classes in ISC? No other classes? Okay. Okay. No other class, no other ISC classes. Okay, we will. So just tell me. Let me see if I can note it down. Yeah, tell me again. So when did you say Friday and when? Friday, 11:30 to 1, and what else? Which other day? Wednesday. No, Wednesday. Okay, and what other someone else? You had an ISC class when? 8:30 to 10 on Tuesday, Thursday. I see. Now, what time is the shuttle from ISC? 11. Okay. And what other ISC class you said? Which days? Thursday. Okay, and okay. Let's see what we can do. I think that is becoming hard because Anupam is teaching 4 classes or something like per week. So he's not being able to shift it. But okay, I'll ask him. I'm going to meet him right now. But none of the others, none of you want to take non-equilibrium or StatMech that Anupam is teaching. The class Anupam is teaching on Monday. You're taking that, and you're also taking this. I see. Okay. And is there anybody else who wants to take both? Are you the only one? He said there were 3 people there in his class who wanted to take this class. Oh. Anyone here who would have liked to take the class if there was no clash? Nobody. Are you sure you're the only one? Sorry, tell me your name again. Saurabh, you're the only one. You're sure? He said, Anupam said there were more than one person. He's not taking. Is that because of the clash? No, he's not taking. He's just not taking QFT. Okay. So is the clash only affecting you? I'm sorry, but is it yeah. Okay? Okay. So one possibility which is not ideal, but one possibility, if we can't find out, if we can find a solution, we'll find it. Is that you watch the recorded lecture for Monday, and we. Okay, that you just tell the academic office because they are recording it, so they should be able to upload it. That we can do faster. So we'll just do try to upload the lecture immediately. That's one possibility. We'll try and find a solution if we can. But if we can't find any solution, then we'll just this is also a possibility to consider, which is not ideal. I understand. I'm sorry for that. But so we'll try to work something out. Okay, but that's one possibility. Okay, fine. Okay. Okay, guys. Then yeah, we'll also need to have some extra classes some days because we're going to miss some. Saturdays works for you guys generally? Can you come? You come to ICTS or you to come? Okay, it's not ideal, but once in a while. Yeah, not maybe one or 2 weeks we'll do Saturday classes. Okay, fine. Okay, sounds good. Okay, so that's the logistical part. Is there any other logistical thing we should discuss? Like not academic, but logistical thing about class timings or something else? Okay, fine. Sounds good. Okay, good. So then what? Okay, are there any questions from last time? Or if you understood everything? There must be some questions, no?
Excuse me, sir.
Go on, yeah.
So, sir, in the last time what you taught in the Peskin and Schroeder, there's a line that we see the behavior of the integral that we evaluated.
Yeah.
With the method of stationary phases.
Hey, give me 1 second because I can't see you right now. I'm going to try and switch the thing. 1 second. No, mic is working, but they have the wrong view. I don't know why they put our own picture. Yeah, sorry, go on, please. Yeah, we'll fix the AV, but in the meantime, please go on. Yeah.
So it is said that the asymptotic behavior for that particular integral is like x square much greater than t square, well outside of the light cone. It says like that, and we evaluate the integral with the method of stationary phase.
Go to the gallery view so we can see who's asking questions. So we don't want to see ourselves anyway. Oh, I hope for recording they are able to record while keeping this other view, right? That's not a problem. Just check that. Yes, I'm very sorry. They're just doing some things to the Zoom setup. So
no problem, sir.
Yeah, it's just some teaching problem.
You are not audible, sir.
Put it on the charging. Already charged. Okay, I don't know. It stopped working. Okay, yeah, go on, Sagar. Go on with your question. I'm sorry you got interrupted. Yeah.
Sir, the thing is, when we evaluated the integral, we considered the condition that r square was much greater than t square, right?
Yeah, yeah. No, we
So
didn't consider that for evaluating the integral. We had an exact expression for the integral, and then I said even in that limit.
yes, right. So this condition that r much greater than t, it is like outside of the light cone, right?
Much outside the light cone. R greater than t is outside the light cone.
Yes,
R greater, even R, yeah.
Yeah. So before beginning of the calculation, we considered that in time t, the particle shouldn't propagate outside the light cone, right?
That's right.
So maybe it's a naive question, but I am not. I'm a little bit confused right here.
No, that's why the formalism doesn't make sense to talk about single particles. The point of this was to show that if you try to speak of if you try to do single particle quantum mechanics, the way we've done it, and you say there's a position eigenstate x, that formalism doesn't make sense because it allows the particle to propagate outside the light cone.
Okay, so it contradicts the theory. That's why we say like this, right?
Yeah, that's why we're doing field theory as opposed to just trying to take single particle. I mean, there are many reasons, but anyway, in the case of dynamics, as I said, we would have to have infinite number of degrees of freedom. But even a free particle, single particle quantum mechanics doesn't make sense.
Okay. And this, they also mentioned that we evaluate the integral using the method of stationary phase. It is a mathematical approach, or
you're looking at Peskin and Schroeder.
Yeah.
I gave you an exact expression for the integral.
Yes, right.
Evaluate the integral by looking at a book of integrals. But you can evaluate it in the large R limit by doing a saddle point approximation. But the Bessel function was an exact answer.
Okay, got it, sir. Got it. Thank you.
Okay. Okay, good. Any other questions for last time? No, I didn't say single particle excitation is not possible. I said you can't. Yeah, if you look at a local excitation, it's never a single particle excitation. You can have a single particle, it won't be localized. If you think of a localized excitation, we'll come back to it maybe in a few lectures from now. You can indeed think of localized excitations, I said, where you have a local where you have an excitation one part of space, and that excitation doesn't grow faster than the speed of light. But that excitation will never be a single particle state. What is the confusion? So far, I have not said anything for you to decide whether what I said was correct or not. I'm just saying this is what we will reach in a few weeks from now. Yeah. So far, we've not even seen phi of x. In what we said last time, there was no phi of x, right? Okay, so when we see phi of x, we can ask, but so far we have not seen anything about phi of x. And if in last time we were just discussing the question of quantum mechanics with a single particle, which we said doesn't make sense. Now, what will happen with phi of x? Let's postpone that question because right now there's no phi of x. There will be soon, but it won't become quantum mechanical for some time. So maybe you can ask me the question again. Okay, are there any other questions? Yes. Okay, good. Sounds good. So let's go on. We spent a lot of time already on this. So we want to discuss today the problem of fields, yeah? and we want to see how fields will help us solve these problems. What we have said so far doesn't logically lead to the conclusion that the only way you can go forward is fields, but it kind of motivates the fact, right? Because that's how we do relativistic electrodynamics after all, by doing fields. And now, we are saying, well, we'll get rid of particles altogether and just talk about fields, and maybe that will help us build a theory which is consistent. And that indeed turns out to be correct. Okay. And, the motivation for that, after all, would be that, we know there's one theory which is relativistic, which is electrodynamics. And there, the particles are photons, and photons you think of as excitations of the electromagnetic field. So maybe if you think of other particles also as excitations of field, it will help you build something that's consistent with relativity. Okay, so electrodynamics kind of you can think of as a guiding lamppost. Just like electrodynamics could have been a guiding lamppost for constructing special relativity as well. Yeah. Okay, good. So we will consider a field, and let's call this field phi of x. Okay, this x is a 4 vector. So this is our field, okay. And this is what's called a scalar field. The reason it's called a scalar field is that this field is now some degree of freedom, okay, and it takes on a number at every point in space time. Okay, so remember this x is there's t and there's x, and you give me some point here, okay, and what does this field do? This field says you give me the coordinates of this point, I'll give you a number. Okay, so this field is just a machine which takes a point in space time and assigns a number to it. It assigns a number to every point in space time. That's our basic degree of freedom. Sometimes it will be convenient for us to separate space and time, especially in the early few lectures. And when I do that, I will try and adopt this kind of notation, okay, where I'll denote the x by a vector x, and then I'll denote t. Sometimes I might write phi of 0x, and then when I separate this, you should understand I'm talking of time separately and space separately, and especially in the early part of the course, we'll do that many times. Okay. However, in general, this is the field that we are talking about. Okay. And this is what's called a scalar field. There are other kinds of fields. The electromagnetic field, for instance, is a vector field. There are Dirac fields. The gravitational field is a spin 2 field. It has 2 indices and so on. But we can learn a lot of field theory just by thinking of scalar fields. Okay, sounds good. So now we have to describe this field in some way that we can generalize easily to quantum mechanics. Okay, and how do we do quantum mechanics? You should remember. Yeah, this is a Lorentz scalar. That's right. This is it has everything to do with it. That's why it's the fact that it's a scalar is saying it's giving you a number at every point, right? When we talk of scalars and vectors, what do we mean? We mean, if I do a Lorentz transformation, are there 4 numbers which kind of transform into each other the way they 4 vectors do, or is there just one number? This is just one number at every point in space. It's not a list of numbers. It's not a matrix of numbers. Okay? So it's a Lorentz scalar. Okay, good. So we want to make a passage to quantum mechanics, and at least the way we understand how to go from classical to quantum mechanics is that we want to write down a Hamiltonian or a Lagrangian formulation for the system, and from there we know how to make a passage to quantum mechanics. In field theory, it's often useful to start with a Lagrangian. Why a Lagrangian? Because a Lagrangian often makes Lorentz invariance manifest, as we will see, and then we'll make a passage to a Hamiltonian, and then we'll go on to understand quantum mechanics. Yeah. So the first thing we want to write down is a Lagrangian. Okay. And the Lagrangian we want to write down as the integral of some Lagrangian density. And the advantage of doing this is that, as you know, a very fundamental object in quantum mechanics, also in classical mechanics, is the integral of the Lagrangian with time, which will now become the integral of the Lagrangian density over all of space-time. Okay, so the idea is that you try and write down some Lagrangian density that's consistent with Lorentz invariance. Okay? And if you do that, then you'll get an action. The action will involve the integral of the Lagrangian density over all of space-time, and thereby you will get a manifestly Lorentz invariant chain. Okay? Now, what kind of Lagrangian densities can we write down? In principle, you could write down anything, but we'll start by examining, Lagrangian densities. Okay, you can write down anything. So you can write down Lagrangian densities that depend on the field phi and that depend on derivatives of the field phi. In principle, we could write down Lagrangian densities that also depend on higher derivatives of the field phi, but we won't consider that for now until much later in the course. Okay? And so we want to consider Lagrangian densities that depend on first derivatives of the field phi and on the field phi. Now, what kind of Lagrangian density can you write down? Well, in principle, you could write down anything, okay? But we'll start by examining the simplest kinds of Lagrangian densities. This is a little bit of a disappointment. In fact, I remember when I learned field theory, it was a little disappointing that we were considering Lagrangian densities that were kind of so simple. Okay, and because when you study class 12 physics, you start considering all kinds of force laws, which are very complicated and do all sorts of things, and then you want to consider more and more complicated force laws. And by the time you come to graduate school, you start going back to considering the simplest kinds of Lagrangians and Hamiltonians. Okay, but that's because field theory is already very complicated. And in fact, as we'll see later, there's a deeper reason why at low energies, the kinds of Lagrangians we are considering are indeed ones that describe the world around us well. Okay? So, for instance, a Lagrangian that we could consider would be this. Okay. This has the form of the kinds of Lagrangians that you have seen before, okay, which look like kinetic energy minus potential energy. Okay. Why does it make sense to write down a Lagrangian of this kind? Because there's nothing very deep about it. It's basically the first quadratic term that you can write down that's Lorentz invariant. You want to write down something in the derivatives, so you take d mu phi, but just d mu phi by itself is not Lorentz invariant. So what do? Well, you have to multiply another d mu phi. This d mu phi squared, by the way, means this. Okay, I'm assuming that you're familiar with some of this relativistic notation, but if you're not, just correct me and I'll try and make this more explicit. But that's what d mu phi squared means. Okay, and then we did that, and then we could have written down something that was linear in the field. But generally, you can get rid of linear terms just by making a shift of the field, just by saying, instead of using phi, use phi plus constant. Okay? And there's, of course, just a constant term we could have written down, but that's not of much interest for the dynamics. And so this is the first kind of quadratic term that you could write down. Okay? So this is the kind of Lagrangian that we'll spend the first few lectures studying. And then, of course, there could be a more general potential for the field. And this potential is something that we'll call V of phi. Okay, so this is an example of some kinds of Lagrangians that we can write down for the field, and of course, we'll spend a lot of time discussing these kinds of Lagrangians. We'll first spend time discussing just this Lagrangian without any V of phi, and then we'll add a V of phi and see how dynamics comes about. Yeah. Okay, so is the general physics clear, right? What we're doing is we're saying, well, instead of particles, the basic degrees of freedom are now these fields. These fields live at every point in space-time. And you want to describe the dynamics. How do you describe the dynamics? By writing down the Lagrangian. What can the Lagrangian do? It can depend on the derivative in the field, and this is the simplest kind of term you can write down. Okay. Okay, good. So what's the first thing we want to do? I want to start by studying classical field theory. So I want to spend some time, most of today's lecture, just discussing classical fields, okay? And then we'll start quantizing them. But for now, let's just discuss classically what happens. Okay? So what's the first thing that we have? Well, we have the action. The action looks like integral L d4x, as I said. Okay? And we want to understand how the equations of motion look like. That's the first thing you want to understand when you do classical physics. Right? Okay. How do we derive the equations of motion given an action? Exactly, right? So you do a variation and you demand that your action should not change under variations. So what happens when we do this? Well, there's a specific Lagrangian I wrote, but let's just consider the more general expression I wrote on top. Yeah, this one. Okay. Okay. So let's say we consider that general expression. Now what do we want? What we want is, we want to ask, what is the change delta S under a small change under phi goes to phi plus delta phi. So let's say you change the field phi by a small amount. How much does the action change? Okay. So when phi goes to phi plus delta phi, what happens to d mu phi? Okay, d mu phi goes to d mu phi plus d mu of delta phi. Is that fine? D mu phi is not really something that's independent. Right? It's a derivative of phi. So if phi changed by this, that's how d mu phi changed by. Okay. How does delta S change? Remember, we're going to work to first order in delta phi. Okay. So how does delta S change? Well, it changes by delta L by delta phi times delta phi this is a derivative, okay, plus delta L by delta of d mu phi times delta of d mu phi. Is that fine? So phi depends on L depends on phi and on d mu phi, and this is how delta L changes. Okay. Now if you look at this term has the property, this is of course d4x, yeah, that you can integrate it by parts. So you can write this whole thing as delta L by delta phi, okay, minus d mu of delta L by delta of d mu phi, okay, times delta phi, okay, and then plus something which looks like the total derivative of the whole thing, plus integral d4x, the total derivative of delta L delta d mu phi delta phi. Is this fine? Yeah. Okay. Notice how the Lorentz indices line up correctly. When you take delta L, you differentiate it with d mu phi, you will get something with an upper raised index. So this whole thing is a scalar. Yeah. Okay. And what I've right now what I've written is just an identity. It's just something which is true. Okay. Now we can choose to consider variations You see, what is the action principle? The action principle is telling us that, under all possible small variations, the equations of motion, if you look at the equations of motion, they have the property that the action is invariant to first order under all possible small variations, right? So in particular, if you consider variations which are small, which are small and which vanish at infinity, I'm free to consider such variations, right? Then this term doesn't matter. So consider variations which vanish at infinity. Okay, and then if I do that, then this term goes away. Okay, okay. What am I left with? Well, I'm left with two terms, both of which depend on delta phi, and which have this form, right? So what I'm left with is something which looks like right. Okay, but now this is supposed to vanish for every possible variation delta phi. Okay. If it's supposed to vanish for, so let's say this was non-zero in some places and zero in some other places. Right? You might have said, well, okay, maybe it's non-zero in some places, it's zero in some places, and it kind of balances out. That when you integrate with delta phi, you always get zero. But in fact, that doesn't work because you can always choose a delta phi that's kind of non-zero at some small region of space-time. And if you do that, this tells you that it can't be that this quantity is positive sometimes and negative sometimes, and that's how this integral becomes zero. But it must be that this quantity is pointwise zero. Okay, so that gives us our first result, which is the equations of motion, which is a very important result, is our del L by del phi is equal to d mu del L by del mu phi. Okay. So that's our first very important result that we find. That's a very general result. It's not only true for that Lagrangian, but it's true for any kind of Lagrangian that you write down. Okay. Okay. So this is a very fundamental result, and this is the first result we already found for classical field theory. Is this clear? Had any questions about this? Okay. Let's do an example. Okay. So the example that we want to do can be for that Lagrangian. So let's see what the equations of motion here are. Okay. So the equations of motion here, what's del L by del mu phi for this Lagrangian now? In fact, let's do it in the case where v of phi is 0. So what's del L by del mu phi? Okay, it's del mu phi. Okay, it's del mu phi because this is half of del mu phi squared. Okay, when you differentiate it, there are two factors of del mu phi. Okay, so this is d mu phi with an upper mu. Okay, so if you differentiate this, you get d mu of del L by d mu phi is equal to d mu phi, which is also sometimes written as box of phi. And if you write this out, in full glory, it looks like d squared by dt squared minus nabla squared of phi. Yeah. Okay. What is del L by del phi here? Here it looks like minus m squared phi, okay, minus v prime phi. If there is a v, if there isn't a v, then it just looks like minus m squared phi. Yeah. So what are the equations of motion? Well, the equations of motion become box plus m squared phi is equal to minus v prime phi. Okay. In the case where v prime phi is 0, so this is called a free scalar field. For a free scalar field, and free scalar field is just a word, and it just means that this potential v of phi is 0. Okay. The equation of motion looks like box plus m squared phi is equal to 0. Okay. Okay, so that's our first example already of an equation of motion.
Sir?
Yeah.
So the term in the brackets is 0 because delta phi is not 0.
Which term? Where?
This last expression of delta s.
This term?
Yes, yes.
Yeah, delta phi.
Above it.
We can choose delta phi, right? So delta
Yes, it is
phi
an arbitrary.
huh?
It is an arbitrary thing, right?
Delta phi is arbitrary. That's right. What is the principle of least action is the statement that the action should be stationary with respect to arbitrary small variations of the configuration space, right?
Yes.
So this should be 0 for all choices of delta phi. And the
Correct.
only way that can happen is if this is pointwise 0.
Yes, understood.
Yeah. Okay. Okay, good. Are there any questions about this?
Is the symbol m because it will be related to mass, or is it?
Indeed, the symbol m is because it will be related. Oh, thank you for that. Good. So this m is indeed, what will be related later to the mass of the particle. Okay, that will mass of the particles created by excitations of this phi. Although at this point, since we haven't talked about particles or anything, this m is just a parameter. But indeed, it's used. It's used because later, when we find a particle interpretation for this field, this m will be related to the mass of the particle.
Okay, thanks.
Okay, thanks. Okay, good. Any other questions? Okay, good. So now, okay, so what's the next thing we want to do? The next thing we want to do is we want to write down the Hamiltonian corresponding to this Lagrangian. Why do we care so much about the Hamiltonian? First, actually, because the Hamiltonian is something that's physical. The Hamiltonian is really the thing. It's the energy. It's something that matters. But the Hamiltonian is key for us to be able to make a passage to quantum mechanics, right? Because in the basic thing that appears in the Schrodinger equation is the Hamiltonian. So to make a passage to quantum mechanics, we need to understand what the Hamiltonian for this system is. Okay. Okay, good. Now, to get the Hamiltonian, remember the Hamiltonian is not a function of d mu phi, generally just of derivatives of phi and phi. In particular, the Hamiltonian depends on the conjugate momentum to phi and on phi. Okay? It can, by the way, depend on the spatial derivatives of phi, but not on the time derivative of phi. Okay? So when you do the Hamiltonian formulation, you trade the time derivative with the spatial, with the conjugate momentum, and then you write down some Hamiltonian that depends on the conjugate momentum and on the fields phi. Okay? Let me point out that, what are the, so let me just make this point a little bit clear. So you want to get the conjugate momentum to phi. This conjugate momentum is not the momentum that has anything to do with this position x that's appearing inside phi. Okay, so this has nothing to do with x. The momentum is just a general term that we use, in that when we say we have a degree of freedom, there is a conjugate momentum which obeys, certain Poisson brackets in the classical theory, and which in the quantum theory will obey certain commutation relations. Okay, so you want to find the conjugate momentum to phi. Now, let me, before we do this, let me just say one thing. What are the basic degrees of freedom for this theory? Okay. The basic degrees of freedom for this theory x. How should you think of this theory when you think of what the basic degrees of freedom are? It's true that we wrote down a field that was a field in space-time, okay? But that is a little like saying, you have a single particle and you think of its trajectory everywhere in time. So you think of its world line x of t. Now thinking of the world line might be useful. In fact, if you have seen the action for a relativistic point particle, the action for a relativistic point particle involves an integral over the world line of the particle, right? But the basic degrees of freedom are just the position of the particle at a point. Okay? In the case of the field theory, the basic degrees of freedom are just the fields at a certain instant of time. Okay? These are the degrees of freedom. Okay? You see, di phi, which is the spatial derivative of phi, is also just a linear combination of the degrees of freedom. Okay? But now when we go to the Hamiltonian formulation, we want to trade the time derivative for a different degree of freedom, which we'll call the conjugate momentum. So this conjugate momentum is denoted by pi, okay, and it has the property that it's given by differentiating the Lagrangian with respect to phi dot. When you do that, what do you find? Exactly, right? In this case, okay, this is the general definition of the conjugate momentum. Okay, for the free scalar field, phi at t equal to 0, x is just phi dot of x. And this is also, of course, true at other times. Okay, so the conjugate momentum is the time derivative of the field. Given this, how do you find the Hamiltonian? You see, to find, sorry, yeah, same as in classical mechanics. But what do you have to do? You see, the Hamiltonian is given by, looking at pq dot minus L. Okay? Here, we don't have a single degree of freedom, rather we have an infinite number of degrees of freedom. So what we do is we look at pi of x, okay, pi dot of x. I'm writing 0 here for time. Okay. Now, but we have to integrate this over all positions in space, not over all positions in space-time. Okay. Notice, by the way, you'll already see a difference between the board on top and the board here, which is the moment we've gone to the Hamiltonian formulation, we are having to separate out space and time, because that's what the Hamiltonian formulation does. And that's why the integrals you're seeing here, you're seeing this t equal to 0 and you're seeing integrals for d3x, which we didn't have when we were just talking about Lagrangians. Okay. Minus the Lagrangian, okay? But let me remind you, the Lagrangian is the thing that we wrote there. which is the one in the top line. It's just the integral over space of the Lagrangian density. Okay? So this Lagrangian, okay? So this is the general definition of the Hamiltonian. Let's see what happens in the case of the free scalar field when pi was itself phi dot. In that case, what you find is, so everything to the right of this line is now for the free scalar field. This is the general definition. I'm drawing a line and I'm explaining what's happening to the free scalar field. Exactly. 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 As you do summation over I in the discrete case, this has become an integral. Exactly. So is this all clear to people? Have you all seen this? If it's not clear, you should stop and ask me. That's exactly right. But,
Sorry, why are we looking at momentum at t is equal to 0 only?
Yeah, so we need to identify the degrees of freedom. When you do that on a time slice. You can of course look at the momentum at different points of time, but the way the formulation is set up is that you identify the degrees of freedom at one instant of time. You can choose that instant of time, and then you evolve it up and down using the Hamiltonian.
Okay.
This equation is of course true at other times as well. The only reason I'm writing this is that I wanted to write the Hamiltonian, and the Hamiltonian is something where you pick an instant of time. You can pick any instant of time. The Hamiltonian is conserved in this case, but you have to pick an instant of time. It's not something that involves an integral over d4x. So I'm just choosing to pick the instant of time, which is called t equal to 0, where it's some arbitrary choice of t.
Okay, got it.
Right, instead of 0t.
Yes, that's correct. That's correct. Oh, so where am I getting this to? Sorry, excuse me, please. Sorry, give me a second, please. There I go. I'm in a class. Yeah. What happened? No, I can't move the car right now. Sorry, you have to ask them to wait because I'm giving a lecture. So they have to wait for 45 minutes. They'll have to wait till 1 o'clock. I'm in the middle of a class. Just please. Sorry, I got distracted. Yeah, go on. Yeah, there was some question. Yeah. Yeah. Yes. Yes, it would be conserved. Yes, that's right. But you have to do the integral over d3x, not integral over d4x. 0, by the way, doesn't mean anything. We haven't chosen origin of time. So of course you could have chosen any other. You could have chosen time 10, whatever that means. Yeah. Okay, are there any other questions?
Is this the reason that the Hamiltonian is not manifest in Lorentz invariant because we take a different time slice for Hamiltonians?
Yeah, that's right. So the Hamiltonian, you pick a certain. Of course, this theory is Lorentz invariant because you started with a Lagrangian that was Lorentz invariant. But the Hamiltonian is that's right. You pick a certain space-time splitting, and then you write down the Hamiltonian. But of course, whatever answers you get will be Lorentz invariant.
Okay. But it's not manifest, right?
I mean, whatever. It's pretty manifest. But yeah, you're right. You break
Space time to space and time.
Yeah. You break space time to space and time. That's right.
Yeah.
Yeah. It depends on what you mean by manifest. But yeah. Okay, are there any other questions? Okay, fine. So now I want to explain what the Hamiltonian is for the case of the free scalar field. See, in the case of the free scalar field, this is pi and this is phi dot, but phi dot itself is pi, right? So this is just pi of x 0x squared d3x, right? And now we want to, we have phi dot squared, right? But that phi dot squared also looks like pi of x 0x squared by 2. Okay. Notice that this whole thing is inside a minus sign. okay, and then we have you see why this has come about? Okay. You see, I took that d mu phi squared and I wrote it as phi dot squared minus the gradient of phi squared. Okay. When I did that, you see phi dot, then I replaced with pi. The reason I did that is because in the Hamiltonian formulation, you're supposed to have only pi's, not phi dots. So you're supposed to replace phi dots by solving for them in terms of pi. That's why I wrote phi dot squared as pi squared. Everything is at 0x actually. X squared minus m squared. Yeah. Okay, is this clear? Okay. But now notice this term just cancels. So what you'll get, and the minus signs also all work out. So what you'll find will be half integral pi of x0 squared plus nabla phi squared. There's a half outside plus m squared phi squared. Okay. So that's our Hamiltonian for the free scalar field. If there was a v of phi there, then the v of phi would just enter here as a plus v of phi. Okay. Okay, is this clear? Okay, now that we have already this Hamiltonian, so is all clear? And we have a momentum, we could in fact, in principle, proceed directly to understanding how to quantize the theory. Right? Because what does quantizing the theory mean? It means you look at the phase space, you parameterize the phase space by phi and by pi, right? And then you just impose canonical commutation relations. And when you impose canonical commutation relations, you have a Hamiltonian that just gives you the quantum theories. Right? However, it's convenient before you do that to use a slightly different parameterization of the phase space, and to parameterize the phase space using slightly different variables, not using pi and phi. So the parameterization we want to do is a slightly different parameterization that, and I'm going to say something right now that is also useful, will also be useful later, is which is okay. So you want to parameterize the phase space as the set of solutions of the equations of motion. Okay. Have you seen this before? Okay. So when you think of phase space, usually you think of phase space in terms of momentum and position. Okay. Let me just say something here. I'm about to say something right now which is not strictly necessary for what we're going to do. Okay. But it's just something that's useful to know, and it's very simple. That's why I'm saying it. But if you get confused and you're looking back, if you open a QFT textbook, you will never see these words. Okay. And you don't need to understand them strictly for what we're about to do. Okay. But what I'm about to say is useful. You see, usually we parameterize phase space by saying, here's phase space, this is P, this is X, right? This is a point in phase space, right? And maybe there's some constraints in the phase space, but there's some point in phase space, right? Okay, good. However, notice if you're given a point in phase space, you can evolve it forward. It'll obey some trajectory. It'll do something, right? It'll keep going like this. So if I'm given a point in phase space, I can use it as initial conditions, and I'll get a solution to the equation of motion, some unique solution to the equation of motion. Okay. On the other hand, if I'm given a solution to the equation of motion, if I'm given this trajectory, I can take a section. I can look at where the solution is at time 0 or at some other time, and I'll get a point in phase space. Okay. So there's a one-to-one map between points in phase space and solutions of the equations of motion. And in fact, you can think of the phase space as being parameterized by solutions to the equations of motion. Okay. There's a one-to-one map. Why is there one-to-one map? Because a point in phase space gives rise to a solution by a Hamiltonian evolution. Okay, and a solution gives rise to a point in phase space by taking a section. A section just means we evaluate the solution at some point. Yeah. Oh my God, unbelievable. Listen, do not disturb, but if somebody calls me some number of times consecutively, then I get a call. Hello. I'm in a class. Please don't call me right now unless it's very urgent. Is there an emergency? It's like Murphy's law. I don't usually get phone calls, but if I'm in a class, then I get like people call me multiple times for some car being moved and okay, okay. So sorry about that. Yeah. Okay. Yeah. So this is why there's a one-to-one map between set of all equations of motion and points in phase space. Yeah. Yeah, the point is that a point in phase space, you don't have to know the Hamiltonian for this. All you have to know is that given a point in phase space, there is a unique solution that goes through that point. So given a point in phase space, there's a solution that will go through that point. So the set of all solutions of the equations of motion gives you a set of coordinates on the phase space. That's all I'm saying. Instead of using P and X, you can use solutions of the equations of motion. So if I know how to parameterize all solutions of the equations of motion, that's enough. Yeah. No, they have to. Because given a point in phase space, you get a solution. Given a solution, you get a point in phase space. So there's a one-to-one map. For every point in phase space, there's a solution. And for every solution, there's a point in phase space. So it cannot be that the solutions do not explode. If you look at the set of all solutions, huh? No. Let's say I give you the set of all solutions to the equations of motion, all solutions, which I parameterize in some way. That is the same as the set of coordinates on the phase space. Okay. So there's a one-to-one map. So this is actually useful sometimes when you do general relativity, because the set of solutions to the equations of motion gives you some covariant coordinates on the phase space, as opposed to using pi and x.
Sir?
Yeah.
So is it like saying that if we know x and p at certain instant of time, suppose t1,
yeah,
then can we generalize to can we generalize to this time evolution of p of t and x of t like that?
Can you what?
Can we generalize to it like p of t and x of t, their time evolution, equations? Is it like that? If you know some instant of time, p and x, can we get its time evolution in general? That's what I'm asking.
You can get it, but that's not the point I'm trying to make here. You can using Hamiltonian evolution. All I'm trying to say here is, if you give me a parameterization of all solutions to the equations of motion, that's the same as a parameterization of all points in the phase space.
Okay, got it.
That's because every point in phase space gives rise to a unique solution. Whether you can calculate it or not is not the concern right now. We just know that there is a map. That's all we are saying.
The solution is a flow on the phase.
It does, but what I'm saying is not very deep, guys. It's very simple. There's nothing. Just think about what I said here. If you have two sets and there's a map for every point on one set to the other set and a map on both ways, then those sets must be this, there's a one-to-one map between, there's a bijection. Here is it. Given a point in phase space, you can generate a solution because you can take this to be initial conditions for a solution. Given a solution, you can find a point in phase space just by evaluating the solution at t equal to 0 or at some other time. So you see there is a bijection between points in phase space and solutions of the equations of motion. There is nothing very deep about this. It's a very simple fact, but it's just something you should know. Yeah? Okay. The reason I'm saying this here is because it's convenient for our field theory to choose slightly different solutions of the equations of motion. Yeah. And the solutions that we want to choose, slightly different coordinates in the phase space. And the coordinates in the phase space you want to choose are coordinates which correspond to a parametrization of the solutions to equations of motion. Okay. So we now want to understand what are the solutions to the equation of motion. Yeah. Okay. So now we'll start looking at the free theory, because that's in fact the one that we can solve the equations of motion for in general. Of course, there are other theories which are not the free theory. But now we're going to spend some time just understanding the free theory. Okay. So what were the equation of motion for the free theory? Right? And we want to understand how to solve these equations of motion. We want to write down all possible solutions of the equations of motion. Okay. If you write down all possible solutions of the equations of motion, then we can get coordinates points in the phase space. Yeah. Okay. So the way we write down all possible solutions is, once again, we write this as d by dt squared minus nabla squared plus m squared phi is equal to 0. Okay. And then it's convenient to just go to Fourier space. Okay. So if you go to Fourier space, by that I mean, we have this field phi, right? So we Fourier transform it. You take both sides, you multiply it with e to the I p dot x, and this must also be 0. So I haven't done anything. I had an equation of motion, and this equation of motion holds at all points in time. Okay. Now I'm just going to Fourier space. Okay. So what happens when you do this? Well, the equation of motion that you get here. So the point is, first, how does this nabla act? Okay. So let's say phi of x. Let me just get my sign conventions right. 1 second. Minus is sign convention. Sorry. Okay. So if you write phi of x into e to the minus I px phi of tx as phi of p, then this minus del squared will just become a plus p squared in Fourier space. Equation of motion you will get will just look like d by dt squared plus p squared plus m squared into phi of pt. Do you see why this happens? Okay. The reason this happens is because you have a nabla squared. Okay. And this nabla, the way it acts on phi of t e to the minus ipx is it pulls down some factor of, it just pulls down this factor ip when you act on the derivative. Why are we leaving our time? Because we want we want to understand how these things evolve in time. You're right, we could have Fourier transformed it all at one go and we would have found the time evolution. It's a little, we don't have to. We could have done the Fourier transform all the way, and then we would have found an equation that looks slightly different. Let me just solve it this way and I'll come back to, of course, you could have done everything at one go. Yeah. Okay. I just want to explain why this nabla squared when it acts on the Fourier transform, it just pulls down some factor of p. Okay, and therefore you get some equation of motion that, you know, in terms of this Fourier transform variable, looks like d by dt squared plus p squared plus m squared into 5t is equal to 0. Okay, are you familiar with these properties of Fourier transforms? Okay, good. This has some simple equation of motion. Okay, and the solution is just that phi of tp. Once again, let me get my sign conventions right. Looks like a of p e to the minus I omega pt, okay, plus a of minus p star times e to the I omega pt, okay, and I'll put a, let me not write an integral here, 1 by square root twice omega p. Okay, okay, let me just explain some things I did here. Huh.
P phi of p comma
Shouldn't it be
dq p phi of p, there's the second line.
here? Huh.
How did del square go inside?
How did del squared go inside?
Take it as pi del square.
So I had this equation of motion, right? Then I wrote this way. I just multiplied it with e to the minus ip dot x for some choice of p, and I did this integral. Okay. Then, you know, if this is the definition of 5, are you worried here? This is the definition of 5 tp. Okay. So when I do this integral, I integrate this by parts, and the del square which acts on phi, I can make it act on e to the minus ip. Okay. And when you do that, you will find a minus ip, one more minus ip, so you'll get a minus p squared. There's a minus sign here, so it will become plus p squared. Okay, is it not clear? You know what's happening here is you have del phi e to the minus ip dot x d3x. So you integrate it by parts. You're always allowed to do these integrals by parts because these are, you know, these fields are not really functions, they're really distributions. And so you can kind of assume that terms at infinity and so on drop out. So this looks like phi with a minus sign times del of e to the minus ip dot x d3x. This del just pulls down a factor of ip. Okay. You have a minus sign here, but this will not matter. So you just get ip into phi e to the minus ip dot x. And that's phi of p. And then you get two factors of ip, and that's why you get minus p squared. Combined with this minus sign here, you get a plus p squared. Is it clear to everyone how this came? Okay. Yeah. Okay. Good. So see, now we found, the solution to the equation of motion, and this is just a simple equation of motion. And what's the solution? Well, the solution is just an exponential because you have d by dt squared plus, some number is equal to 0. So that this number, you just put up here in the exponent, and this omega p is just square root of p squared plus m squared. Okay. If you just choose omega p to be this for every value of p, this is giving you a solution to the equation of motion. Now I've done a few more things. First, you see, the solution could be e to the minus I omega p, or it could be e to the plus I omega p. Okay. Now what I did was, you remember there's a hermiticity condition on the field. We didn't say it so far, but it's actually true, which is that phi of tx is equal to phi star of tx. Yeah. This is the condition that the field is a real variable. Okay. In terms of momenta, that translates into phi of tp is equal to phi star of t minus p. That happens because the way we defined phi of tp was with an e to the minus ip dot x. Yeah. And so when you take the conjugate, you also invert this. So that's why I wrote this as A of P plus A star of minus P, not as A star of P. That's because you want phi of P star to be phi of minus P. Okay. You see why I wrote A star of minus P? Okay. These two are just solutions of the equations of motion. You see, these are the only two solutions of this equation of motion, right? If you have d by dt squared plus x squared plus some omega squared, this is a simple harmonic oscillator. Then I multiplied this by 1 by square root of twice omega. Why? Because I felt like. And that's actually the, it will be useful as a normalization, but in fact, you don't have to. Yeah? At this level, you don't have to. This is just a choice of normalization that we are choosing in order to make our life a little simpler as we go forward. But at this point, if you said, I don't like this factor, I just want this to be the solution, that would be fine. But then the APs that you would be using and the APs I would be using would be different by this factor. That's fine. Okay? At this point, there's nothing telling us we should choose this. Normalization is just something that will make life simpler as we go forward. Okay, it's just a number. Okay, is this clear why we got these solutions of the equations of motion? Okay, good. Very good. Now,
What are the APs?
APs are just numbers.
Okay.
Yeah, they're just some things that parameterize the solution.
Yeah.
Yeah. Okay, good. So given this, okay, I'm trying to get my conventions right. So given this, we find that phi of x tx looks like it's a sum. So you have to Fourier transform back. That's phi of tp. If you Fourier transform back, you'll get phi of tx, right? So it looks like AP times e to the minus I omega pt e to the ip dot x plus AP star e to the plus I omega pt e to the minus ip dot x. Okay. Okay. There I wrote it in terms of A star of minus P. Okay. But when I Fourier transform, when you Fourier transform, you should, here we define pi of Tp with e to the minus ip dot x. So here I should put e to the plus ip dot x. But you see, you're integrating over all p. So I could have written a of minus p and put plus ip dot x. But because it's an integral over p, I chose to write a of p and e to the minus ip dot x. Is it clear why I did this? Yeah. Okay, so this is our answer now for the field as a function of space time. Okay, good. We can also write this as a of p into e to the I p dot minus I p dot x plus a of p star e to the plus I p dot x with d3p by 2 pi cubed square root twice omega p, where these guys are 4 vectors. Yeah. These guys are now 4 vectors where this p looks like omega pp and of course x looks like tx. Yeah. And this 4 vector p obeys the property that p squared is equal to m squared. Yeah. By the way, somebody asked why we couldn't. Okay, is this clear? And I'll explain this thing. Yeah. So this is called the Marsh shell condition in terms of 4 vectors. It's the same solution. All these are equations. This is equal to this, equal to this. Is this clear? Yeah. Okay, good. Now, someone said, you know, why couldn't we have Fourier transformed in time? You could have, if you Fourier transformed in time as well. And then you would have found this condition. You would have found, well, your solutions had to satisfy p squared is equal to m squared on that. And this is indeed what you would have got if you Fourier transformed in time. You could have. Yeah. Okay, so these are solutions of the equations of motion. And we see that the solutions of the equations of motion are parameterized by these numbers AP and AP star. These are parameters on the solutions of the equations of motion. Is this clear to everyone? Okay, good. Are there any questions about this? All clear to everyone? Okay, sounds good. If there are questions, like, stop and ask. Okay, good. Oh, I should have noticed you get a 2 pi cube came there because that comes in the inverse Fourier transform. Okay, good. Yeah. Given that solution of the equation of motion, actually, space. We can in fact make this map also explicit in this case. Right? You see, what are the coordinates in the phase space? They're phi at time 0 and pi at time 0, right? Is this fine? There's no t here. Yeah? Is this fine? This is just phi at t equal to 0. What's pi? Somebody? It's what? It's phi dot, that's correct. And then, so in terms of this, very good. Okay. An omega term will come, but there will be also something different. Apart from the omega term, is it just omega? Should I just write omega times this? Very good. Right. So two things will happen. First, you'll get an omega. Right? There's also a factor of I. Okay? But apart from the factor of I, what happens is you get a minus I omega for this, okay, and a plus I omega for the AP star. Okay. So we find that this term looks like I omega or minus I omega. One of the, it also cancels. There's also an omega which there. So it'll look like minus I omega by 2. Depends on, yeah. And then you get an AP times e to the I p dot x minus AP star e to the minus I p dot x. Okay, whether you get AP minus AP star or AP star minus AP depends on where you chose the sign. I chose this sign to be minus. Okay. 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 Now you can invert these relations to get AP and AP star in terms of phi and pi. Okay. And how do you invert those relations? Well, you just invert them by realizing that just take this x, multiply it with, let me get my sign conventions right, e to the minus I p dot x, integrate it. Okay. What happens if you do that? You see, this p here is actually a dummy variable. I could have written this as p prime. So what happens is you get e to the I p prime dot x, e to the I p dot x, d3x. You see that? Remember, there's a Fourier transformation identity which is e to the I p prime minus p dot x d3x is equal to 2 pi cube delta. Okay. So if you do that, then this just pulls out the p terms here. Okay. So you just get AP plus AP star A minus P star. One by square root twice omega p. Yeah. And similarly, if you take pi of p equal to 0, x, multiply it with e to the minus I p dot x, you'll get minus I omega p by 2 into AP minus A minus P star. Okay. Okay. Clearly, you can use this to solve for AP, right? You add the two equations, you'll get AP. You subtract the two equations, I mean, after putting the right factors, you'll get A minus P star. Okay. So you can use this to see, you can use this to solve for phi and pi in terms of A and A star. Yeah. Let me just write down the solution. Maybe I'll write in a different board. Okay, I think I got my factors of I right, but please check. I'm going to write down an answer, but I want all of you to go back and check and make sure that the factors of I and minus signs are correct. Okay, it's just some linear algebra now. So this is the answer that I have. Okay, so AP looks like square root of omega p by 2 into integral phi of x0, phi of 0x, e to the minus I p dot x d3x plus I by square root twice omega p phi of 0x e to the minus I p dot x. Okay, and AP star, that's of course just the conjugate, square root omega p by 2 0x x x minus I by square root twice omega p phi of 0x e to the I p dot x. Okay. Okay. You should go back and check that I got my minus signs and I's right. I think I did, but just go back and check. Okay. So you see, given AP and AP star, actually given AP, okay, you can use it. Of course, you can put it in the formula above and get pi and phi. Alternately, given pi and phi, you can use it to get AP and AP star. This is what we were saying, what's written on top. which is that you can parameterize phase space either in terms of pi and phi, or in terms of AP and AP star, which are of course solutions of the equations of motion. Notice these operators AP and AP star are not Hermitian, that's why it's AP star. Okay, right now they're not even operators, they're just numbers, but these are complex numbers. AP is a complex number, and AP star is its conjugate. Okay. Okay, good. Are there any questions about this? Okay, in fact, I wanted to do quantization, but we're out of time and I'll have to go at 1. So I'm going to stop here. I just want to review what we did, and then next time we want to quantize it. Of course, when you quantize the fields, what do you want to do? You want to impose the canonical commutation relations on phi and pi. So you want to write phi pi is equal to I. Okay. When you do that, we'll find some nice set of commutation relations in terms of AP and AP dagger, which you promote these two operators and you'll find some nice set of commutation relations for that. And that will lead us to the Hilbert space for this theory and what we get. Okay, let me just summarize what we said today. Okay. What we said today was, we said, look, we have a field. Last time we discussed why we need fields. And today we wrote down the simplest kinds of Lagrangians we have for fields. Why Lagrangians? Because that's what helps us maintain Lorentz invariance. That's what helps us understand relativity. That's what helps us go to quantum mechanics. And we said the Lagrangian we write as the integral of a Lagrangian density. We looked at what the equations of motion you get in terms of that, which is an important result. It tells you that d mu of del L by del mu of del mu phi is the same as del L by del phi. Then we looked at a specific example, which is a field, a simple scalar field. And for that we worked out what the equations of motion are. For the case of where the potential is 0, which is called a free scalar field, the equation of motion just looks like box plus m squared phi is equal to 0. That's an important equation that you should know. Then we solve that equation, you get some solutions that look like that involve this omega, which looks like square root of p square plus m square, which controls the time evolution for all the momentum modes. And then we said, look, you can parameterize the phase space of this theory in terms of the field and its conjugate momentum, or alternately in terms of this AP and AP star. Okay. We also have the Hamiltonian, which we also worked out. And next time, we'll impose canonical commutation relations and use the fact that we have the Hamiltonian to get a quantum theory for the free scalar field. Okay. Okay. Are there any questions about that? Yeah.
Could we explain why we're not when you're trying to make the Hamiltonian?
Yes.
Why are we not integrating it over time?
The Hamiltonian is never integrated over time. The Hamiltonian is something that's defined at an instant of time, the same as the Lagrangian is. What we wrote as curly L was the Lagrangian density. Okay, you integrate that over space, you get the Lagrangian. The integral of the Lagrangian over time is called the action. The Hamiltonian is not integrated over time. The Hamiltonian is given at an instant of time. It tells you how the system evolves. The Hamiltonian is some function of the phase space variables, P and X, but P and X at a given time. You never integrate the Hamiltonian over time. If you integrated the Hamiltonian over time, there would be no, that quantity doesn't have any meaning in classical physics. It's not the Hamiltonian if you do that.
Because of Hamiltonian formulation will not manifest in Lorentz invariant. Because we are choosing the definition of phi to be del L del phi dot.
Yeah, you're picking a time coordinate. You see, the Schrodinger equation tells you d psi by dt is equal to h psi. Or alternately, the Hamiltonian tells you how to generate time translations. You say time translations, you have to decide what time. You have to pick a time. You're right, that also went into the choice of pi. When you said pi, you picked a time, but basically when you do the Hamiltonian formulation, what you're saying is you have some Hamiltonian, and that tells you how to generate time evolutions. But you have to tell me which time, whose time. The Hamiltonian corresponds to the energy, right? But the energy is not some Lorentz invariant concept. You have to tell me energy as measured by whom. You always have to choose a time coordinate to define a Hamiltonian.
Can parameters using proper time?
Proper time of what? Of whom? There's no particle here. There's a field, right? So there's no particle here. So there's a Hamiltonian that you have to write down, and when you write down the Hamiltonian, you have to write down. You see, I emphasize there's no particle here. There's a field which lives at every point in space-time. When you write down a Hamiltonian, you have to choose what is time and what is space. There are other choices possible which are related by Lorentz transformations, and the Hamiltonian will transform nicely under them. But you have to decide which one you're talking about. This is something that people say many times, But in fact, the Hamiltonian not manifest, but it's not such a big deal. And we shouldn't. Sometimes some textbooks make very big deal out of it, or Lagrangian is manifestly Lorentz invariant and the Hamiltonian is not, and it's kind of true. But it depends on what you mean by manifestly. Like the Hamiltonian transforms nicely, and everything is Lorentz invariant in the end.
With respect to derivative of time with respect to derivative of phi with respect to time, we have a phi. Why don't we have with respect to space variables?
It's not something that you see when you talk about dynamics in classical dynamics. You talk about coordinates, you talk about positions, and some dynamical variables, and their time derivatives when you set up phase space coordinates, right? So P is given by the phase space coordinate with respect to the derivative of the Lagrangian with respect to x dot. Here the different variables that you have are phi's at different points in time. Sorry, what I said, right? The different the different degrees of freedom you have are phi's at different points in space. Okay, del I phi is just the difference. It's just some rewriting of the degrees of freedom. It's like saying rather than using qi for different particles, I chose to use q1 minus q2, which you could do. That's what del I is doing. Del I is just taking the difference of phi at different points. So the basic degrees of freedom are phi at t equal to 0 and x. Okay, and del I phi is just a rewriting of those degrees of freedom. So in the Hamiltonian formulation, del I phi is like, you can use del I phi instead of phi. It's just some transformation of variables. Rather than using q, you use q1 minus q2. Okay. But q dot has a more fundamental meaning. Okay, so P is the conjugate momentum, and when you write down commutation relations, you impose commutation relations between P and x, not between q1 minus q2 and q. Okay. You could write down something which is del L by del mu phi, but that's not what you'll impose commutation relations with. That's not what will have nice Poisson brackets. You see, why are we doing this momentum thing? We want to quantize the theory. We want to understand what is it that obeys nice commutation relations with phi. And the rules of quantum mechanics are you identify the momentum, and P and x gives you I. What is x here? X here is phi at different points in space. Del I of phi is just a rewriting of that. Just some linear combination of that. So that's why pi is special. It's telling you what time derivatives, and that you always do when you go to quantum mechanics. Okay, are there questions? More questions? Okay, so let's stop here and we'll meet. I'll send a mail. Anyway, we are not meeting this Friday. Whether we are meeting on Monday or not.